Hi, this video continues talking about the quantum numbers of hydrogen-like atoms. And so in the last video, I described the principal quantum number, which is designated little n. And in this video, I want to talk about instead the angular momentum quantum numbers. There's actually two of them. So these two quantum numbers are given the symbols L and m sub L, and the values that L and m sub L can take on are restricted by the value of n, the principal quantum number. And these restrictions, again, are really just given to us during the process of solving Schrodinger's equation. So really, it was given to us mathematically. Okay, so what I want to do is, I want to describe what is the physical significance of L and m sub L, right? And I'm telling you that they're related to angular momentum. So angular momentum in classical physics, when you learned it, I'm not sure what symbol you would have seen, but a typical symbol that's used to designate angular momentum is capital L. It is a vector. And the way you calculate this in classical physics is with R cross P, right? So it's the angular momentum. It's essentially a question of where is the momentum. And it typically tells you about how much material swirl you have, right? So you pick an axis which gives you a way to basically say what is R, right? R is measured from an axis, and you go from the axis out to where you have material moving, right? So the material has momentum out away from an axis, and doing this cross product gives you this interesting quantity called angular momentum, so a material swirl. So if you go and you think about an atom, right? An atom is a little system. We say that the nucleus, which I'll designate with a Z, is down in the middle. It's not moving. And what we have moving around it, though, is electron, right? Electronness. And the Bohr model had a really simple way of saying what the electron was doing. It was just going around in a circle. That was the Bohr model. But the Schrödinger model doesn't assume how the electron goes around. The only thing that the Schrödinger, like the Schrödinger process of modeling the hydrogen atom, the only thing you assume is the interaction energy and basically the spherical symmetry of the interaction energy. And what you can get is, instead of the electron going around in a circle at a well-designated radius, you get a cloud. Actually, let me make it seem like a cloud of electronness. So you get this cloud of electronness, and in the cloud, in a sense, you get the electron to swirl, right? And if you have a swirling sense like this, and if we take the axis to be, say, through the nucleus, right, just through the middle of the atom, then this kind of swirl has this angular momentum vector, right? You use the right-hand rule. So it would be upwards like this, right? So this is the angular momentum. It's just, what's the material swirl? Well, the material that's swirling, because the nucleus stands still, the material is electron. So it's the electron swirl. And in particular, because we imagine the electron not having a well-defined location, the electron kind of exists in a lot of different places at the same time, in a sense. And it's moving in a lot of different directions at the same time, in a sense. So we say that the electron is better represented as a cloud. And so when we talk about the angular momentum of an atom in this quantum mechanical context, we're talking about the material swirl of the electron cloud, right? The material swirl of an electron cloud. So when you go and you look at wave functions, right, which come with these quantum number labels, and you try to understand what does R cross P mean for these various quantum states, these various wave functions, what you find is the following fact. If you ask what is the magnitude of the angular momentum vector, that is, you actually, in a sense, drop any interest in the direction of the swirl. What you only ask how much swirl there is. Let's call this just capital L without the vector symbol. Right, so this is the magnitude of the angular momentum. It's actually equal to, it's a function of the quantum number lowercase l. So that's why lowercase l is called the orbital angular momentum quantum number. And the relationship is kind of a strange one. You take L times L plus 1, so it's an integer times the integer increased by 1. You take the square root of it, and you multiply by h bar. So L is an integer, right? L is going to be an integer. L can be 0, so that is capital L can have the value 0. So the atom can have no angular momentum, which is very interesting. Or, L can be 1. So 1 times 1 plus 1 is 2. So you have a square root of 2 times h bar. That's another possible value of the magnitude of the angular momentum vector. But notice that it's multiplying the h bar. H bar is the quantum of angular momentum. Right? Remember that the dimensions, the physical dimensions of Planck's constant is, you can understand it in terms of energy time, or you can understand it in terms of distance times momentum. Because remember, there is also a Heisenberg uncertainty principle, right? That delta x times delta p is on the order of h bar, right? This is Heisenberg's uncertainty principle. Remember, this also gives the units to h bar, or gives us a reason to expect a certain physical dimension for h bar. It's angular momentum because it's distance times momentum. Heisenberg's uncertainty principle is not about angular momentum directly. I only use it to show you the dimensions. So for that reason, I'm going to erase Heisenberg's uncertainty principle for a second. I'll have reason to talk about it again in a minute, though. Okay, so Planck's constant is referred to as the quantum of angular momentum. Another way that people say what Planck's constant is it's the quantum of action, where action is a very special physics word. But here we'll just think of it as the quantum of angular momentum. So as an example, what if we knew that we were studying, for example, the state n equals to 3, L equals to 2, and m sub L equals to, for example, -1, right? So this means that L equals to 2, and we can say immediately that the value of the angular momentum magnitude for this atom's state is equal to the square root of 2 times 3 times h bar. So square root of 6 h bar. So that's the value of the orbital angular momentum. And L is known as the orbital angular momentum quantum number. Right? Okay, so let's go on. So now we know what the principal quantum number indicates. That's the energy level. The orbital angular momentum quantum number indicates the amount of angular momentum our atom has, but it actually doesn't tell us about direction, right? It's only strictly the magnitude. So what does m sub l tell us? So m sub l is interesting. M sub l is actually related to the z component of angular momentum. And if you immediately say, why is it only the z? What happened to x and y? And why is z special, right? Z is special only because of our spherical polar coordinate system. You remember that our coordinate system actually, in a sense, picked out z to be special, and it kind of made x and y, in a sense, equivalent. So the x direction, the y direction, the z direction. The reason the z direction is special is because if I was to draw a vector, so here's some vector, its projection down in the xy plane, let me say it's projected to here. If you wind around to that direction in the xy plane, we call that the azimuth angle, right? But the polar angle is called theta, and theta is associated with m sub l. So just because of the fact that our spherical polar coordinate system chooses z to be special, this is why m sub l is the z component of the angular momentum. Now you might wonder, does this sort of ruin the fact that we expect nature not to be special in any particular direction? And the answer is it does not ruin it, because you'll find that whenever you do any physics that sort of asks you about coordinate system independent questions, you'll never get a particular direction to be special, right? It's only when you first start by asserting a coordinatization of the space that you're studying does z become special, right? So it's after you choose a coordinate system that z becomes special. Z's not special beforehand. Z's not special in a fundamental way. Okay, so, but anyways, m sub l. So let me say how m sub l is related. So the angular momentum vector, right? It's a vector, so it's got an x component. So I'll use the unit vectors I hat, j hat, k hat. So it's got a y component, and it's got a z component, right? And m sub l is about this value. L sub z equals m sub l multiplied by h bar. So this is an important relationship. Actually, let me put it in red. So I'll box it in red, and I'll box this one in red as well. So in terms of quantum number lowercase l, I understand the total amount of orbital angular momentum, but I do not know its direction. But here is a slightly directional piece of information. So it tells me about the z component. Okay, so so there's the z component of the angular momentum. So the idea behind quantum numbers, let me say something slightly generic. Because we can label psi sub n L m sub L, right, as a definite state of the atom, this means that n, L, and m sub L indicate knowledge we can have simultaneously. And what I mean by this simultaneous knowledge of n, L, and m sub L is there is no Heisenberg uncertainty principle against this knowledge. Right? So what I mean by against this knowledge, remember that, for example, delta x, delta p was something like h bar. What this means is that there is a fundamental limit to your simultaneous knowledge about the location and the momentum of a particular sort of object in a system, right? Heisenberg's uncertainty principle is an unavoidable factual limit on knowledge. But if we want to know the energy, the magnitude of the angular momentum, and the z component of the angular momentum of an atom, we can know all three of these things with arbitrary precision, unlimited by any uncertainty principle. But what is true, though, is we cannot know, for example, Lx and Lz. That is, there's going to be an uncertainty principle between simultaneous knowledge of those two things. And actually, interestingly, right, this is an angular momentum and this is an angular momentum. So if I product amounts of angular momentum, I've got to have angular momentum squared dimensionally, right? So there's more to this than what I'm writing, but there is an uncertainty principle between simultaneous knowledge of uncertainty in momentum in x, angular momentum in the x direction, and the uncertainty of the angular momentum vector in the z direction, right? So you cannot have simultaneous knowledge of two different components at the same time, but you can have simultaneous knowledge of the total amount with no direction knowledge and only, honestly, z, x, or y direction knowledge. But it's most natural because of the polar angle theta being special to z. It's L sub z is the natural one to know. Okay, so all right. So let's go on and think about angular momentum a little bit more, just some definitional things. So first definitional thing is historic orbital sort of shape labels. So these are known as the S, P, D, F. And so these, like the S orbital, P orbital, D orbital, F orbitals, I refer to these as shapes. And then they keep going. There's the G, H, I, J, K, L, M, N, O, right? So they just continue out. But what they actually correspond to for our single electron hydrogen atoms is actually the value of L. So S is L equals to 0. P is L equals to 1. D is L equals to 2. F, the F orbital, is L equals to 3. Right? So, yeah. The interesting thing about L equals to 0, is this implies that our atom has no orbital angular momentum. if we have no orbital angular momentum, what does this mean? Does this mean our electron is always at the location 0? Does this mean that our electron always has momentum 0? Right? Because that's how you get 0. Or does this mean that the location of the electron is always in the same direction as the momentum of the electron? Is the electron always headed either outwards or inwards from the nucleus? So none of those are going to be true, right? So what does L equals to 0 mean? It means that if you think about your atom, right, which has a cloud of electronness, what this means is that you're as likely to discover your electron to be swirling this way as swirling that way, right? It's got no overall swirl, right? That means it's equally likely to be discovered swirling this way as swirling that way, right? So the electron is simultaneously, anywhere you look, headed towards the left and towards the right and upwards and downwards, all in the same amount. So we say this this orbital configuration, or this shape for the electron orbital, is spherically symmetric, right? So there is no overall angular momentum. And when L equals to 0, since m sub L, it only has one value, right? 0. Yeah, so this means that there is no z component to the angular momentum, is what that means. Okay, so let's go on and talk about, let's see, I'm just looking at my notes real quick. All right, so here's another really interesting, strange idea. This is called space quantization. So for an example, let's choose any value of n such that we can have L equals to 1. And so L equals to 1 means that m sub L can either be 1, 0, or minus 1, right? That's what I have. So I'm considering this is a p-shaped orbital, right? So a p orbital. If I draw my coordinate system, so let me draw a coordinate system. I'll do it in black. So this is the z-axis. Actually, it's not going to fit here. So let me draw it here. So the z-axis is upwards. The x-axis is sort of out of the screen towards the left. And the y-axis is out of the screen but towards the right instead. And here is something interesting. So L equals to 1. This means that the magnitude of L, right, is the square root of 2 h bar. That's what that means. And m sub L means that L sub z can either be negative h bar, 0, or h bar, right? And if you recall, square root of 2, actually, let me not put it there. The square root of 2 is about 1.414. So L is actually bigger than L sub z, right? So 1.414 h bar is bigger than, let's say, the magnitude, right, of L sub z. So you can see that that's true. So what this means is, and also actually, Lx squared plus Ly squared, right? It's equal to L squared minus LZ squared, if you think about it, right? So this is just the Pythagorean theorem. The sum of the squares of the components of a vector add up to be the magnitude of the vector squared, and I just subtracted the z component to the right-hand side. So L squared is twice h bar squared, right? Because L is the square root of 2h bar, and L sub z is, for example, for m sub L equal to 1, right? L sub z is h bar squared. So I'll be subtracting, for example, for m sub L equals to 1, right? That's the case of L sub z equals to positive h bar. You just have this. What I'm trying to say is Lx squared plus Ly squared is greater than 0. That is, but I don't know what Lx or Ly individually are. I just know that their squared combination is bigger than 0, which means that because I don't know what Lx and Ly are, but I know that they're important, I'm not really sure how to draw the L vector. So I'm just going to draw the L vector the following way. I'm going to say that the L vector is a vector that exists somewhere along this cone. Because if you take a position on the cone and you drop an altitude to the xy plane, that's got a particular value of Lx and a particular value of Ly. And that vector, let me draw it in blue, is the angular momentum vector. But I do not know where its shadow is in the xy plane. I don't know where its shadow is, but I do know it has a shadow in the xy plane. What I do know as well, though, is the size of the angular momentum vector in the z direction. That is, I know this value right here. This value is h bar. Another possible value, though, let me draw it on the next page, is m sub L equals to 0. So this is L equals to 1, m sub L equals to 0. And what I have in that case is, so I'll draw, here's the z-axis again, x, y. If m sub L equals to 0, then that means that L sub z is equal to 0. That is, Lx squared plus Ly squared is equal to L squared, right? But I don't know anything about Lx or Ly. So I'm not sure which way the angular momentum vector points. I just know that it's pointing out somewhere along that circle. So let me show you an example of a possibility. Here is a possible angular momentum vector, but we know its Lz value is 0. So here it is. So the previous example had Lz, right? This is Lz, Ly, Lx. It had the it had Lz equal to h bar, right? And we had this cone specified here, right? But the other m sub L is -1, right? So this is L equals to 0. Not L equals to 0. L equals to 1. M sub L equal to -1. So that must indicate another cone down below along the negative L sub z axis and its intersection with that axis. So let me draw the axis down below. So there's the rest of the cone, or the back behind the cone. And then this location, let me draw it in blue again. Right here is negative h bar. So from the side, let me clear this up a little bit. You can draw a picture that looks like this. So this is LZ, and then this is some combination of LX and LY, right, or a perpendicular direction to Z. And for L equals to 1, we can only have H bar, 0, or negative H bar for the L sub Z values. But the L vector needs to have a length of square root of 2 H bar. So the L vector has to point somewhat, right? So that is the L equals to, or M sub L equals to 1, L vector. This is the M sub L equals to 0, L vector. And this is the M sub L equals to -1. So I'm referring to this as space quantization, and the reason I'm referring to this that way is because this is the only set of answers that you'll get if you were to measure the angular momentum of your atom, right? If you knew, let's say you knew your atom was in the L equals to 1 or p orbital shape, then the three possible M sub L values that you can get quantum mechanically is 1, 0, or -1. Those are the only things that you'll see as the outcome of experiments where the experiment depends on the value of the angular momentum. And that's the sense in which the space is quantized. You only get these particular angles. So this is the square root of 2 H bar, and this side right here is H bar. And if you look, this is a little triangle, and this is the polar angle theta. Can you see that the cosine of theta in this particular case is equal to, right, it's the adjacent over the hypotenuse. So the adjacent is H bar, and the hypotenuse is square root of 2 H bar. So 1 over the square root of 2. And you can get theta is the cosine inverse of 1 over root 2, right? You can also get, in this case, square root of 2 H bar is the length, but M sub L equals to 0, so there is no, right? That polar angle is 90, right? So this is the polar angle for M sub L equals to 0. It's 90 degrees. Oops, I should put degree symbol up there. Yeah, so this is beginning to look at the sort of space quantization, or the angular orientation quantization. It only angularly orients in space. That is, you'll only ever discover it to have one of these three values if you know you're dealing with a p orbital, right? Okay, so how would you measure angular momentum? And this is the last topic of this video. Let's think about this for a second. Let's say that I've got an atom, right? So here's my atom. And let's say that its overall electron swirl is this way, right? So that means that M sub L, for example, is definitely, say, going to be positive, right? It's not 0, and I'm saying it's positive because if this is the z direction, this is actually the L sub z component, just by the right-hand rule, right? If you calculate r cross p for, you know, my electron is swirling towards the right, and here is the little r vector, right? So you imagine r cross p with a right-hand rule, and you'll get an upwards angular momentum vector. So that means the L sub z component is bigger than 0, which indicates that M sub L is also bigger than 0. But all this is to say, this is electron motion. So if electron motion looks like this, then what this looks like is a current loop where we have electrons moving this way. But if electrons are moving that way, then we understand negative charge moving towards the right as the same as positive charge moving towards the left. So that's the direction of the current. And if I have a current that's moving that way, then the kind of magnetic dipole moment I get, symbolized by mu, is downwards. Can you see that the L vector points up? The angular momentum vector points backwards to L because the charge that's swirling is actually negative charge. And that's why the magnetic dipole moment has to be opposite to the angular momentum moment. Okay, so all of a sudden, we re-understand our little atom. Our little atom in P, D, F, these are orbitals where L is going to be bigger than 0, right? It has angular momentum. Our little atom in these PDF style orbitals, where angular momentum is not 0, our little atom is actually a space quantized magnet. And this space quantized magnet can respond to external magnetic fields. So this is one way that you could see the magnetism of an atom, or the the space quantized orientation of an atom. Okay, so I'm going to stop this video here, and yeah, this turned out to be a long video.